Hi, I hope this video finds you well. Today we are looking at leak code number 438, find all anagrams in a string. So essentially the main task is you're given two strings S and P, and we're tasked with finding all of the anagrams of P that are contained within S. However, we are supposed to return a list of the indexes from which these anagrams begin. So we have ABC. We can see that CBA is an anagram of ABC because you can rearrange the letters and get the same you can rearrange the same letters and still maintain both of them. So, or the same frequency rather. So when you're talking about anagrams, you're really concerned with the frequency of each character in the same amount. And so CBA can be rearranged to get ABC, and so these are anagrams. But the first solution, I mean, the solution isn't the string itself as such, it's really just the indice from which it begins. The other one is A, B, or actually I believe it's somewhere in here. It's BAC. Now, BAC is an anagram of ABC and so forth, vice versa. And this index actually starts at 0, 1, 2, 3, 4, 5, 6. So 6 would be the second solution here. And so we've returned a list with 6. Now, the idea here is that it seems to be based very closely on another problem, which is called, this one is called permutations, right? So this one is permutation in string, right? So the idea here was you're given two strings, S and S2, S1 and S2 rather. We're returning true if S2 contains a permutation of S1. So here you have S1, and then here you have S2. If you can rearrange S1 in whichever way, or even keep it as itself, and find that within S2, we're tasked with returning true. Now, so what was the idea with permutation in a string? We first begin by judging whether or not their lengths are consistent. So what do I mean by consistent? Well, I mean that if S2, which is supposed to be the longer string that's supposed to contain a permutation of S1, if that in length is not adequate enough to accommodate the length of S1, well, then we know that you can't have a permutation if there's not enough space in that string to contain all of the letters of the permutation you're trying to assess. And so we say that, S2, if S2 is less than S1, or rather if S1 is greater than S2, however you want to see it, we return false off the bat. Otherwise, we have a frequency array, right? So we have a first frequency and second frequency. The first frequency is of the first string, and the second frequency is of the second string. And so we use basically this idea of creating a table, basically of where the indice correlates with the alphabet. So 0 is A, 1 is B, 2 is C, and so forth. And then this for loop in particular, it is able to loop through the first string S1, and it will gather a frequency, right? So first freq stores the frequency of A and B, right? So it'd be 1 and 1 at position 0 and 1. And then we also populate the second frequency table with the frequency of S1. Now the difference is that throughout this algorithm, first frequency is not going to change, right? So the frequency, this is our anchor here, right? We're going to constantly refer back to what first frequency is. And trying to assess whether they're the same, whether second frequency and first frequency are the same. Because the idea is that we're going to take a sliding window of the length that matches S1. We're going to take a sliding window through this string S2, and then the frequency array is going to update, right? So the frequency array, it starts, we can assume it starts from here, and then I will have I's position will be incremented and D's position will be incremented. And then we're going to ask, does that array match S1? And it wouldn't, because S1's frequency array would have one increment on A and one increment on B. And then S2's frequency array has one increment on I and one increment on D. These are completely different positions, right? And then we move the sliding window along, right? So we would evict I from the window, and we would obviously follow that up by reducing I's position, the increment of I, we would decrement it. And then we would increment the position of B. And so now we're comparing D and B, and does D and B's frequency table match, does the frequency table of S2 now match the frequency table of S1? And so forth, and it wouldn't, right? But eventually we would evict D and we would add A, and B would have a count of 1, A would have a count of 1. And so S2's frequency table would match S1's frequency table, right? And so we've done this, right? So we go through S1 dot length, grabbing the frequency of the first character. The first characters, really. We go through the shorter string and we grab the frequency. And then we ask ourselves, well, okay, for that first window, are they equal? And then being equal is if every entry across both arrays is the same, then they would be equal. If they're equal, we'll return true off the bat, right? Our first window was successful to give us sort of something that matches. In this case, you can see that our first window doesn't, right? So what's our new window? Our new window would start from, so the sliding window is actually applicable to this bigger string, right? That's where we're doing the sliding window. And so here, E and I, we've checked and they're not equal. So we evict E from the sliding window, and then we add D to the sliding window. So we evict E and then we add D. So now the array has an increment at I, which was 1, and then we have an increment at D, and we've decremented the position for E. And so we constantly move like this, right? And so that's kind of what we're doing. So the sliding, after having checked the first window and checking the validity of that window, what we're doing is the right pointer, that's when we start this is the sliding window algorithm. That's where we start the sliding window technique. And the right pointer is it needs to start from, the right pointer, the next window that we would look at is this one here, like this, right? So coming into the while loop, the right pointer is on the character that, let's see. Coming into the while loop, R is positioned on the indice that matches the length of S1. So it's actually positioned at D, right? Because that's the character that needs to be added, right? If you look at this next window, D needs to be added into the window. And so coming into the while loop, R has assumed that we are on the character that we want to add, right? And so, and it is, right? So R is equal to S1 dot length. You might think that's 2. Well, it's not. Well, S1 dot length is 2, but the indice 0, 1, 2. So R is actually on the third character, right? And so it adds, the frequency table, which changes, which keeps into account what the frequency is of characters as we move along, as we have this window move along this string. It adds, that character that R is referring to, right? So the frequency table now goes to whichever position stores D, and it adds 1 to it, right? So it does that, but then it decrements, the table. We go to position E, we decrement that because we intend to evict it, right? And so now we're looking at this window, right? And so now that we've updated our frequency table, well, let's reassess, right? Let's say, okay, well, is the first freq and second freq, are these tables the same now at least? And you return true if it is, right? And so to set it up for the next iteration, we need, R should be pointing to B and L should be pointing to D, right? So D and B, L moves up by 1, R moves up by 1. And so now we're looking at a new window, right? And so we come back up here, we say, okay, well, let's remove the end, and then let's add the new character. So remove the end, add the one that's incoming, and then check again, right? And so you constantly keep checking, right? You constantly keep checking, and you keep doing this until you come across, in this particular case, until we come across BA. And BA is sort of, it contains the same amount of characters, right, as S1, and these are both the same. So the arrays are equal, right? And so we return true immediately. So that's permutation in string, right? But if we look at find all anagrams in a string, this question, if you kind of gloss over the code between both of these questions, right? They, let's look at the similarities here for a second. We seem to have the only real difference is, we're returning a list, and that should be obvious here. And we're still hashing both strings, right? In the same way we were doing this before, we're still hashing both strings. But we're still iterating between both strings, right? We're still iterating. And then we also check if they're equal or not, right? But in this case, if the first window has an equivalency, then we simply add the index, right? So we're adding the index of that first window, of the beginning of that first window, which is 0 always, right? And then of course, we get our left and right pointer for the sliding window. R points to s1 dot length. It's coming into the sliding window. It will point to the incoming character, right? And then same thing with left, right? Same thing with left in the sense that they're both 0. They both start at 0. And so what that allows us to do is R is positioned on the character we intend to add, which is what we do. L is positioned on the character we intend to evict, which is what we do. And then we reassess, are they equal, right? And so same idea here, right? We decrease and we increase so that we're positioned on the characters we want to remove and add. And if they're equal, it's only a difference of what we do if they're equal, right? In this case, we're adding left plus 1. So why are we doing, we're not returning true. Of course, we'd want to add, maybe you would think we should add the leftmost character, right? But that actually doesn't make too much sense. It has to be left plus 1. And that's specifically because if you think about it, right? So coming into this while loop, right? And it might even be better to maybe pull up an example, but coming into this while loop, assume that we're looking at, so we've removed a character from the end, right? And L currently, the left pointer currently refers to a character that we are intending to remove from the window. Okay, and then R is positioned on the next part of the window, the character that we intend to add. And so we do end up adding it, right? So as far as the array is concerned, we've removed from the window the leftmost character, and we've added the rightmost character as far as the array is concerned, right? The frequency tables rather. But by the time we come to check, right? So now that we're checking sort of the equivalency between these tables, right? L hasn't actually had a chance to update. So L still actually refers to the character that we intended to remove, right? So you can think of it here like maybe, yeah. So I think this might be actually a good, well, maybe not. Yeah, actually, well, no, because we took care of that case. Let me go ahead and give you an example that would probably make better sense. If we had, so let's suppose we had this string here, right? But instead it was like this, right? So the equivalency is here. Okay, so basically what would have happened is like, okay, we would have stored the frequency of them both. The list wouldn't have contained 0, right? Because this first window doesn't actually have a solution. It's this window that has a solution. So the index wouldn't be positioned on, that's not a valid solution. So we're tasked with finding the indices of the anagrams that are contained within the larger string. And so since we don't have that in the first window, 0 wouldn't be one of the solutions, right? But coming in, R refers to the character that we want to add to the window, which is A. So we do add A to the window, right? So A has a count of 1. B already had a count of 1. And we've decreased C because this should really be Z, I guess. And so we've decreased Z, so that's no longer in the mapping as well. But we've introduced C. So C, B, A now have 1, 1, 1. Their arrays are equal, right? The P hash, the hash of the both strings are equal, right? The tables, the lookup tables, sort of, they're equal. And so but you can imagine that as we do this, right? So as we have just done this, the arrays know that they're equal, but L hasn't actually had a chance to move up. L is still positioned here. We have taken L, right? We've taken L and we have used it as a way to cut off the end from the array, but L still points to Z. L doesn't get a chance to actually move up until after the judgment, right? So if you want to say, okay, well, I want this string, I want the beginning of this string, it has to actually be L plus 1 in order to actually do that, right? So what you'd want to do is you'd actually want to say, okay, well, and if we'll go back to that example, right? Which is this one. What you'd want to do is you'd want to say, okay, well, coming into the array, I know that R is on the character that we're gonna, and I'll change this to Z and this to Z like we had before. Coming into the array, Z would actually be evicted, right? Because we evict it from the array. The array no longer considers any presence of Z. It's 0 now. And then we add the character that, the character of the next window, right? And then so after we do that, L should move up, right? And R should move up. R could also move up, right? But now L actually does look at the beginning of this of the string, right? Of the substring. Before it wasn't, right? Because before, if you remember before what was happening, right was looking at right and left both, right? So we were doing right plus plus and then left plus plus. So as far as the arrays were concerned, they knew what the equivalency was, right? And that's why we returned, why we would return answer. We would return left, but we would actually have to do left plus 1 because left actually didn't get a chance to increment before the judgment, right? It's still tagged on to the last character, to the other end of the window. And so L has to have a chance to move up in order for you to reflect left or L rather, whatever you call it, has to move up before before the judgment, right? And so that's why in this case it would probably make sense to say left plus plus R plus plus or right plus plus left plus plus before before the judgment, right? Because them actually moving up doesn't have anything to do with the judgment. I could set right equal to 100 and left equal, I would get index out of bounds probably. But the fact of the matter is that regardless of what right and left is, this is specifically only concerned with whether they're equal, and then I get to add what that left was. Okay. So they're both the same, except some of these things to keep in mind.